So welcome to our second revision tutorial on allotropes of carbon and giant covalent structures. And the second giant covalent structure that we're going to look at here is graphite. So the first thing that's worth noting down is that graphite, again, is an allotrope of carbon, which means it's made up of carbon atoms in a specific structural form. Okay, so it's an allotrope of carbon. Now, whereas previously you've looked at diamond, graphite is slightly different. Now, we noted that the similarity obviously here is that it's made exclusively of carbon atoms. But whereas in a structure like diamond, where there are 4 carbon atoms bonded to another carbon atom covalently, in graphite you have around 3 covalent bonds per atom. So it creates a slightly different shaped structure. So 3 covalent bonds per atom. So it creates a slightly different shaped structure in that it creates hexagonal structure. So it creates a hexagonal structure. But just bear in mind that obviously the covalent bonds between each of the carbon atoms are still strong covalent bonds. So whereas obviously diamond has 4 covalent bonds per atom, that means because graphite has 3 covalent bonds per atom, there is at least 1 delocalized electron per atom. Now, that's important because then when we are talking about differences between graphite and diamond as allotropes of carbon, it means that actually graphite can conduct electricity. So it can conduct electricity, and that is due to these electrons, these delocalized electrons within structure being able to move around. So these E minuses just represent the free electrons that are able to move around. And as we say, there are 1, 2, 3 covalent bonds per carbon atom. Now, as well as being able to conduct electricity, because the electrons, there are delocalized electrons, it means the electrons can also transfer thermal energy as well. So in that respect, it's easier a substance to heat than diamond. Right. Now, we create these layers of graphite, and when we're talking about one single layer of graphite, that is referred to as graphene. So graphene is what we refer to as a single layer of graphite. Now, it means that when you are referring to graphene, graphene is only 1 atom thick. So it's a very thin substance. So it's only one atom thick, but it still retains the ability to conduct electricity because of delocalized electrons. And it is also means it's a very light and a very strong material. So it can conduct electricity, graphene can, and it's also very light and strong. But when we have layers of graphite, when we have layers of graphene and graphite next to each other, they then form between the different layers, what these dotted lines represent. They have very weak intermolecular, so between molecules, weak intermolecular forces between them. Which is holding them together, but it doesn't mean it holds them together particularly strongly, okay? So it's a giant covalent structure, so therefore you end up with these layers. So it's arranged in a layered structure. But due to the fact that there's these very weak intermolecular forces between them, it means that these layers can slip and slide across each other really easily. So they can be worn away or moved away. And it means that graphite as a property ends up being what you might describe as particularly soft and slippy, because these different layers can move across each other and these weak intermolecular forces can break really easily. Now, because they're soft and slippy, it means they can be used for different substances such as oils and lubricants. And also, if you think about a common tool that you use, pencil leads are made of graphite, so that every time you use the top of the pencil, it wears away and it wears away so that eventually it's disappeared. And that's because these layers of graphite that are made up are being wiped across and wiped away onto your page and removed really easily because of these weak intermolecular forces between them. So that's our brief summary of the structure of graphite. So just to recall the key points, when we're referring to graphite, it's used in things like pencil lead, and each carbon atom forms 3 covalent bonds per structure with the carbon atoms, and it forms layers of hexagonal rings over each other. It is worth mentioning that due to these covalent bonds and the fact that they're strong, it still does have a high melting point. So to break apart these carbon atoms, it still does require a lot of energy and lots of heat. Now, but due to these weak intermolecular forces, the layers themselves are easy and able to slide across each other, and means that graphite itself can be quite soft and slippery, so it can be used as a lubricant. And also because you've got these delocalized electrons moving around within different layers of graphite, it means that graphite itself can also have the property that it can conduct electricity and also thermal energy as well. So that's our next tutorial done on the second allotrope of carbon, looking at graphite.